wonderful cluster of speakers today, along in the whole panel. Some of panelists we have already heard in the cluster 1, but in the cluster 2, we'll be moving forward for the cyber physical systems and emerging technologies. Quickly, this particular slide is showing that who are the luminaries we are going to listen today. First of all, we have senior research scientist, Professor Anuradha from MIT. Then we have very distinguished, I would say, the one of the founding fathers of the LCA, Light Combat Aircraft Tejas program, Dr. Kota Harinarayanan. Then we have Professor Prabhat, and then also we have other august speakers, Professor Rajiv and Professor Chandra. So a brief from the perspective of that what we are talking about in the whole realm of machine intelligence and also the cyber physical system. Where do we fit in from the perspective of Aerospace Technologies Vertical? So here this cartoon particularly shows that there is the whole transition we had seen as a human race from Industry 1.0 to Industry 4.0, where we are today. Most of us are seeing that change. And we are definitely rapidly moving towards the Industry 5.0. We are at the transition. Now, something which really resonates with me and the whole aerospace community. So I would say that one of the key, particular quote, which I always mention in the talks, when I get to talk to students and the practitioners in the AI and in the domain-specific aerospace domain, is that if you really want to get into the autonomy and want to master that, as Dr. Kota was also mentioning about, we need to focus on the optimization, especially from the multidisciplinary optimization perspective. And we want to leverage the Industry 4.0 for making smart industries and smarter factories. So from that perspective, we have to look beyond traditional engineering challenges, whatever we have. So where we have to go then? So two key things where we have to really handshake. So one is the, along with the aerospace and mechanical sciences, the one is the neuroscience department. And secondly, certainly the psychology department. Behavioral sciences is one of the key things we have to really learn from these two particular domains and branches and implement that, translate that knowledge into heuristics and convert that using applied mathematics into tangible, doable products in terms of codes, tools, and techniques using computer science. So when we combine these particular theories and findings, we are on the verge that we are going to optimize our Industry 4.0 knowledge and then successfully transfer to the Industry 5.0. So this particular slide shows the whole transition. On the left side, we have whatever the application of the proven technology we have already done in most of the cases very successfully in the aerospace domain, and especially from the perspective of the smart manufacturing, smart factory concept. And the right side of this whole particular slide talks about the emerging technologies, where we are heading towards as a whole community of mechanical sciences and aerospace manufacturing units, and then where we have to focus towards. So I would like to quickly draw your attention towards on the emerging technology particular front on the first row. That is, today's session is definitely targeted towards artificial intelligence. And precisely, if I have to say, we are specifically talking about machine intelligence. Now, where we have to talk towards is that, can we go using the optimization of the autonomy from the different domains, definitely leveraging and from the cross-interdisciplinary knowledge from computer science. And at descent with the domain knowledge of mechanical and aerospace sciences, can we make the digital twins at a module level, at a component level, or definitely at the holy grail will be at the system level? And then as earlier Dr. Kota was mentioning, so here the transition from the cluster 1 would be that how we can leverage the computer vision knowledge and translate and use that into increasing the remote on-wing care. For example, remote on-wing care for the jet engines, where I had a lot of experience in the Rolls-Royce. And then how we can use especially the remote part. So there are lots of companies, so one of them is Liverstream. So they try to use the borescopic cameras and then try to translate that image to the person who's an expert who's sitting at the other side of the world, and then there we can have the online sessions, and then person can repair then and there itself on wing. We need not to cut down. We need to improve the downtime, so there should be no lag in the operational timelines of the operators. So, there are this slide is a little busy from the perspective. Every one particular block has its own subject. But again, the second row in the second part of the slide, the right part of the slide, again talks about the auto visual inspection, which is again quite motivated from the machine vision, how we can leverage. For example, if we have a high pressure turbine blade, which takes a huge amount of load, think about that one particular turbine blade, which is of this much size, literally of this much size, approximately in a jet engine, and that takes the tip of that blade takes a load approximately equivalent to of a bus, the whole fully loaded bus. So from that perspective, how we can inspect that criticality of the blade so that we should not have any of the damages or catastrophe, we can at least alleviate to the maximum degree, because this is a safety critical domain, as earlier Professor Vineet also mentioned rightly. So this particular slide is briefly talking about that, from the digital twin perspective, there has been successful demonstrations at component level, certainly from the Bosch. I had myself seen that and having conversations with their VP. So, and a couple of companies are really moving towards aggressively. So, and there are lots of interesting literature available online. So, where we have to focus towards in this particular talk. So, so these are a couple of points which I have from my side, which can be considered in the future research and technology opportunities, not only research and development, which is generally TRL, technology readiness level 4 and below. So 4 and above shall be captured by research and technology and the way forward. So and it also captures a couple of questions which our speakers have, our audience have already started asking. So one of them is that we can have our global collaborative clusters for research and technology demonstrators for applied applications in aerospace technologies. And then this is something very close to me, where I've seen that, where we started working towards on one of the projects. We can have a common database of aerospace research problems. So it can be think or like that we can have a Kaggle equivalence of an aerospace or mechanical sciences. So Kaggle is something very common to the computer science community or the AI community. So for education purposes, for research and problem solving with new tools, methods, utilizing data science and machine learning relevance problems. So one of the open source available data. So, we have in our panel, Dr. Parimal is there from NASA. So where, one of the very beautiful example which is available for open source, kind of proliferation is the CMAPS data of the jet engine for the prognostics and health monitoring from the Center of Excellence from NASA Ames Laboratory. So that is a wonderful example. Something of that sort, we have to start really putting that into open source as much as possible. Definitely looking forward and also keeping in the constraints of the security as well as any type of export control issues. So, and industry have already started applying some of them. So we have AI Gym inside the Rolls-Royce, and also the concepts are also being quite successfully taken up by Airbus, and they're already in practice. So third one is on the consortium of industry and research labs and universities. We can have an open research problems and encourage students and faculties and scientists across labs to contribute towards the solution, which is a common problem. So, and as I said earlier, so on the digital twin at a component level or at a module level or at a system level, we can target on something where we have a clear success definition, which shall focus on certain MVPs, minimal viable products, and demonstrators with the technology readiness level mentioned, and then we should target towards that. And certainly we shall look forward towards have a joint PhD programs with nation across the nation, as well as with the other counterparts available across and experts in the different labs and the universities abroad. So in this particular cluster, I so leave the forum to the other luminaries in this cluster and the whole panel, where the focus can be think over that we can focus on the driving applications, which can be digital or smart factories and manufacturing units, design and analysis, or something around the urban aerial mobility, which we can leverage from the perspective of cyber physical systems and emerging technologies. And there are some list of questions which has been already been circulated to the panel. So I will leave the floor to the panel, and may I request Dr. Anuradha to please share her thoughts.
Yeah.
Thank you very much for the invitation to be a part of the panel. May I share my slides?
Yeah, Dr. Please go ahead. Please click the share button at the bottom.
Yes, please.
Okay, all right. Yes, so that was a great lead-in by this session panel chair. So that sort of sets up what I wanted to share with you very well. What I would like to go over are some of the challenges at a systems level. And as Rajneesh pointed out very nicely, we need to really address this underlying problem from various levels, and the systems level is what I'd like to focus on. Our lab at MIT, it basically looks at complex large-scale systems and how decision and control and optimization can occur at different levels. And over the past 3 decades, we've been looking at a number of different domains. Aerospace is one of them, energy systems being another, transportation being the third, and of course, cyber physical systems as a generic methodology and its analysis and synthesis is something that we've been focusing on. Again, as Rajneesh pointed out, so I want to really talk about three things. One is security and resilience, and the second is how do we deal with decision-making in safety-critical systems? And the third is, what's the role of humans, given that we indeed have skilled operators, such as a pilot in flight systems? How do we really address the challenges in the context of cyber physical systems? So the first one being security and resilience. And we are always interested in any aircraft to make autonomous decisions in real time. And given that you're going to have environmental uncertainties, it's a complex problem. But then on top of that, given that we open up the digital domain and all kinds of vulnerabilities that enter the picture, there could be cyber attacks, either at the sensor level or at the communication network level or at the actuator level. And all of that basically introduces significant challenges in terms of cyber physical security. And again, as Rajneesh pointed out, Industry 4.0 really sort of sets the stage and brings these issues a lot more into focus than any other times, with Industry 1.0 being mechanization, or 2.0 being mass production through electricity, and 3.0 being essentially the computer revolution. And now we are really talking about customized digital transformation using big data, et cetera. So what that does is that you have several technologies that basically come together, which is a great opportunity. But the significant challenge here is that it becomes vulnerable to cyber attacks. So at a systems level, and of course, there are many, cybersecurity is not a new topic, but cyber physical security is something that has to be addressed, I believe, during a different set of methodologies. So from that point of view, in aerial systems, I see this as a three-pronged attack. So if you're looking at the impact of any cyber attack, then essentially there are three components in here. Either you could start to delay the effect of the attack, and that is one way in which you can mitigate the effect and introduce cyber physical security. So think of everything that happens before the attack as security, but then it transitions to phase 2, where the attack actually occurs. And so now we're talking about resilience. And so how do you minimize the maximum impact that this particular attack has? That, again, I submit is a systems level point of view. and necessitates appropriate methodologies. And the third one being one of resilience. How do you minimize the recovery time after the attack has occurred so that you figure out what the best way is you can return back to normalcy? So we've been developing methods for all of this sort of three-pronged approach by using concepts such as baiting, and different aspects of machine learning and different aspects of shared control. So I would submit that this is one of the first sort of emerging technologies that needs to be addressed in their cyber-physical systems. And the second is machine learning in CPS. And this is something that obviously is a topic that's taken the scientific world by storm. And no matter where you look, there is some form of machine learning or the other. And so the question is, what is the best way in which we can leverage the tools and the understanding that's been happening in this domain? This itself, I think, is a whole course, not just a 5-minute presentation. So I'm just going to have some very broad takeaways in here. When we say learning occurs at multiple time scales. And that then says that depending upon what the scale is at which you need this learning to occur, we need to appropriately interweave learning with whatever you're trying to do in a safety critical system. Because when you're in mid-flight, you don't have enough time to actually learn what went wrong, perhaps, depending upon the kind of anomalies that we are faced with. And so in order to ensure that you first remain safe, and that is, after all, the first word here that we're looking at, we need to first have some sort of level of adaptation that ensures that your flight is going to be safe, for instance. And another thing which is often missing in the machine learning community is a guarantee when you don't have perfect learning. I mean, what happens if your neural network is not trained properly? And so the very important stuff of putting control first and then learning is something that I think we really need to pay attention to. And this message is really not being paid as much attention by this community as it should. And if you are talking about a fully autonomous system, which is really what Industry 4.0 is, you need to have these real-time decision-making tools. And so in addition to having like an adapt, learn, and remember type of approach, where you first ensure stability and safety, and then use hindsight to learn, and then some sort of a wisdom, if you will, so that you remember what you did before the next time you see similar anomaly, we also need to learn from humans. And so that basically sets up the last thing that I want to share with you, where I submit that in addition to looking at cyber-physical systems, we ought to be really looking at cyber-physical and human systems. Because no matter what we're talking about, again, at the system level, there is a general trend to go from traditional systems to smart systems. There is support enabling technology in the form of data, where we're getting more and more fine, heterogeneous, and distributed data. The kinds of decisions that we are able to make is becoming more sophisticated, so we understand how to design control algorithms with nonlinear, adaptive, and distributed. We are leveraging all of these technologies to start moving from partially autonomous systems to fully automated. But the part that, again, I think we've not really paid that much attention is exactly how you're going to reach this sort of holy grail, if you will, using an understanding of how a human, a skilled operator, makes decisions, because that, again, ranges from a low level to a high level, and we're capable of various high-level tasks of perception, cognition, reasoning, etc. And so that needs to be really appropriately stitched together and develop cyber-physical human system architecture. And this might be either one where if something severe happens, that the human simply takes over, which is quite often the case. And in fact, the Boeing MAX accident is one where it didn't occur properly. A supervised one where essentially the human monitors and provides sort of a high-level set points or other kinds of inputs into automation, and the automation is able to take care of a faster response, and you don't have the usual pilot-induced oscillations. Or it's one which is the most challenging one. How do you actually coordinate the actions that these two decision makers perform in the cockpit in order to get the best performance? And so this is again something that we have to address because smart societies are going to involve a variety of interfaces. So it could be that humans need to be on the loop, and quite often this is basically what is better understood, so that then we really figure out what exactly is the right way to allocate tasks between pilots and autopilots. Challenging, humans in the loop then really have to be more carefully analyzed. So to make sure, for instance, the kind of thing that happened in the German wing situation where the pilot drove the plane into the mountains is something that does not happen. And so some aspects of behavioral models of humans need to perhaps be looked at. And so that I submit is the last challenge that I think is really important at a systems level. So we've been working on all aspects of these, and there are a number of references in here that I'm happy to share with any of you. That's basically what I wanted to say here. Thank you.
Thanks a lot, Dr. Anurag. May I request Professor Dr. Kota to present?
Thank you very much. I want to make a few worries for an aircraft designer, an application of artificial intelligence, especially machine learning, more so the deep learning, because all aircraft today, whatever you produce, need to be certified for their safety. And the deep learning, whatever we have seen, today the decision making is not explainable. You do not know how the the algorithm takes a decision, and as a result, this especially for control systems, where you need to take continuous decisions for a fighter aircraft about what is the next actuation has to be done. Whatever study that has been done, we are not able to work out how to explain how the system is taking a decision. And that is where the question of what you call explainable MLDL is the word is coming up. How do you explain the system is really taking a decision? Okay, this is the number one problem. And until this problem is solved for a manned aircraft, you will not be able to use, even though the algorithms are very powerful, the decisions seem to be good, but we do not know how the decision is being taken. Okay, this is one particular problem which is bothering. The second area where no such problem is there, but what we are looking at is how do I use machine learning for health management, and how do I plan the aircraft preparedness availability. For a civil aircraft, the availability is what differentiates between an aircraft which is profitable to an aircraft which is not profitable. We are now looking at a next generation regional aircraft, and we talk to all the airline operators in India and outside. What they say is you need at least a 50% reduction in the maintenance effort. Now, this cannot be done in the conventional way. We need to use machine learning and apply the machine learning for the health management, both from more so for the prognostics, because diagnostics can be done in a conventional way, but for prognostics, that is where the requirement is. And this is where the algorithm development and proving the algorithm to a level where we can give at least something like 95% of accuracy, that seems to be an issue which need to be looked at. Okay, we have been seeing this in a few cases where the supervised learning is done, and where the expert gives the input and output, and some good results have come. And I think the highest level of maturity has come in case of the gas turbine engines. Okay, but now there is a serious work going on. How do I move from gas turbine to electrical machinery? How do I do that so that my environmental impact is reduced and my energy consumption is also reduced? This is what is the talk. If that is the case, how do I now bring in this machine learning so that the machinery's functioning is well controlled, and the prognosis can be reasonably accurate, whereby whole planning can be done based on the prognostic algorithms. This is the second point we need to look at it. But perhaps the best work that has been done today as far as the health management and using the machine learning is in gas turbines. But we are looking at, can I use it for structural health monitoring? Because now, for example, the aircraft, what we have done, 90% of the surface area is made out of composites. But how do I manage to monitor the health of a heterogeneous material like a composite? That is where perhaps we need to look at it, how to do that. A lot of work has been done on using FPG sensors, embedding the sensors, and bringing out the benefits of that. But still, we are not able to demonstrate very well for a manned aircraft how we can say this will function. And also, how do we manage to measure the the health of the sensor itself? How do I do that? First attempt is, how do I do that? If we can do that one, and we are able to bring it to a level which can be demonstrated to a certification agency or a safety agency, then I think we will be able to move forward. And the expectations of the airline operators or the military will be able to meet. These are some of my comments. I would request my fellow panelists to look at it and see either a roadmap can we draw whereby this can be done in steps. We need not have to done in one go, but can we do that kind of a thing? Maybe a lot of collaborative effort is required from all the groups, lot of research collaboration and validation. Okay, validation possibly we can help, but the initial research collaboration is what I'm looking forward to. I look forward to your suggestions. Thank you very much.
Thank you, Dr. Kota. This was a very succinct and well-put presentation with, I think you have covered a couple of points which can directly go into the recommendations and collaboration area. And may I request now Professor Prabhat to share his thoughts, please.
Dr. Prabhat, can you switch on your video camera? Yes.
Professor Prabhat Hajela.
I'm sorry, I'm on another call, and I had informed Dinesh ji that I was going to be either unable to join or join a little bit later. But I'm going to break away and just make some quick observations for the panel to consider, because I'm involved in another meeting right now and will not be able to join for a longer period of time. So let me just make some quick observations. I think I've been listening in the background to all of the speakers. The things that we really need to focus on, as far as I'm concerned, is in the area of cybersecurity and AI. So this is from two areas in particular. The first one being to detect intrusion, that if your system has been compromised, can you develop AI systems in order to be able to detect that intrusion? The second one, of course, is to have AI techniques in place to guard against that intrusion. So these are two areas in which one needs to focus. But with aerospace applications in particular, and the type of environments you have been talking about, namely drones and unmanned air vehicles and so on and so forth, there are a couple of other things that one must pay attention to. In particular, you're working in an edge computing environment where the computational power that is available to you on platforms that you're trying to work on is limited. Therefore, there has to be a focus on AI algorithms that work in a distributed environment, that work in a resource-constrained environment. So the focus has to be in that area. That also then plays into how different platforms are able to actually optimize the use of power. So if you have limited power, can you actually use distributed platforms, that is to send information back and forth between a platform where information is needed to a base platform in such a way that you can actually optimize the use of power that is available on board. So that is the second area in which AI algorithms need to focus on. Finally, let me just say, I reiterate what Professor Kota, I thought I heard him in the background talk about explainability, and I think other panelists have also spoken about that issue. Certainly in the area of manned vehicles, that is an important criterion. And the last point I want to make is that I think this is a wonderful idea about collaborations, international collaborations, and getting things organized in such a way that people here in the US and other countries can work with our counterparts in India. But as we plan this out, let us be aware that some of us will have export control limitations on us. And our ability to work in certain key domains like this becomes a little bit challenging. So working through universities is perhaps a better option overall. And with that, I'll stop here, and I'll still continue to listen to you in the background, but I'm on another call and I have to get back to that. Thank you again for your attention.
Thanks a lot, Professor VaiBhaV, for your time. Thank you. May I request now Professor Rajiv to share his thoughts, please?
Okay, hello everyone. So first of all, I'd like to thank organizer for giving this opportunity. So I'm going to switch gear. My talk will be quite academic. All right, so this is in our lab. We are looking into these machine learning AI with applications to our CFD and fluid structure interactions problems. So I'm Rajiv German, and I'm faculty at in the Department of Mechanical Engineering at UBC Vancouver. Okay, so what we are looking here, so as we know, this is for our unmanned system. So we have issues about the lift, right? So we looking to study aerodynamics, so it's well established, all these unmanned systems. Other idea is using some kind of rotary motions for these our drones and unmanned system, and also quite well established in everywhere we use them for drones. So in our lab, we are exploiting these bio-inspired flapping mechanism, right? So there are a lot of research is going on. So as I said, I'm looking more basic research point of view here. This direct industrial applications will need to build upon. So what we are looking here is to first understand, so some of our panelists are talking about this integrating AI ML to physics, right? So explainability will come once we really understand underlying physics and how these systems interact with the environment, all right? So this is where we are looking, part of our research is bringing physics into overall this black box machine learning toolbox. So in our research, we are modeling whole system, looking whole couple physical behavior where we have your aerodynamics, flexible structures interacting, and then looking for optimization and control techniques. So what you see here is I'm comparing if you have your rotary and flapping, and of course the rotary type of ideas is you're chopping air and creating a lift. But how about we do this, what birds and bats, they do it. So can we explore flexibility and have certain flapping frequency and create your lift? So in our here idea is to, as I mentioned, so we want to use articulated flexible multi-body wing, exploit flexibility, having some kind of adaptive wingspan, and changing your kinematics. So idea here is to do aeroelastic optimization sensing, having some physics informed your data. All right, so you want to generate data and can look for your control. And in the end, that leads to your efficiency and noise reductions. So we are generating lots of data in this whole process. We are modeling whole bat-like wing. So you got these thin membranes connected with your bones. Those are again flexible, your beams and membranes, and allowing them to just mimic like your bat. So this is again, you have complicated multi-physics aeroelastic system, and we generate data, and then we are feeding into these deep learning neural nets. So in particular, what we have looked into this particular architecture where we do convolution, recurrent, and autoencoder. So there are a number of steps we are looking into how to build these kind of networks, which can learn your whole high fidelity data and scan through, and then you provide all those your control mechanism. So in our research, we are, as I said, this is ongoing research. We are looking, the experiments are done in Brown, so we are looking high fidelity numerical analysis and then integrating with AI machine learning. So on the right hand side, what you see is we got experimental, and we are mimicking, generating all the data, and then building all our AI ML toolbox, which integrates our whole multiphysics analysis. So our objective functions. So here a lot of details I'm not going to explain. So what I want to say, some of the things are working, and we are trying to explain how these your convolution process, how recurrent, all those things we can interpret through physics point of view. And finally, this is nothing new here. Non-linear system identification is already a big area. So this whole machine learning and deep learning in particular can be integrated in that similar kind of process of our this self-reliant Bharat. So first thing is an exciting topic right now is integration of your scientific machine learning with our cyber physical system in the context of aerospace technology. And there are a lot of opportunities for Indian context. And as all other panelists discussed, there are a lot of open questions here in terms of your generalization, how these things are working. What are the physical significance? Here in aerospace, we really need to understand from physics point of view how things are working. In particular, in my area, if I'm talking these kind of complicated your multi-physical behavior, in particular, if I'm looking turbulence and vortex dynamics and complicated process, how to explain for this if you're using this AI now. And finally, can we trust? All right, so this is where explainability and all those concepts. And physics is only way if we integrate and understand underlying physics, and then can we build some understanding through these black box and the like. And finally, there are some issues we need to understand from ethics, accountability, and can we all the decision making we are doing through this AI/ML process.
Professor, can you please conclude?
Yes, so this is a final thing. So yeah, so can we can discuss about those in part of our panel discussion. Okay, so that's all I wanted to share.
Great. Thanks a lot again for setting the tone for the cyber physical system and the emerging technologies so in the context of aerospace sciences by all the panelists in this cluster. So to my understanding and the message which I received from Professor Chandra, I think he will not be able to join because of some unprecedented reasons. So in that, so may I request to move to cluster 3 and request Professor Vishak Bhattacharya to take the lead, please.
Thank you. Shall we start the cluster 3?